Good afternoon and welcome. My name is Robbert Dijkgraaf, Director of the Institute for Advanced Study, and welcome to this kind of town hall meeting about gravitational waves. There was a lot of popular demand of this to discuss and learn more about this wonderful scientific discovery. As you know, we're talking about one of the weakest trembles ever picked up, 1 part in 10 to the 21, but I think I'm right to saying it was kind of an earthquake both for science and in public opinion. I think for many of us, I haven't been to a gathering, a dinner or a cocktail party where this wasn't a topic that was discussed. And so I think it's terrific to spend some time here on this. It's kind of improvised meeting, although we had quite a long lead time. First of all, I think those of us who have went through many of the scientific talks about promises of one day we will discover gravitational waves. So it's a little bit like you go to your friends and they always talk about renovating the kitchen and it never happens. And then one day you come and they have renovated the kitchen and you're shocked. Another way, of course, it's almost to the day 100 years ago that Einstein first predicted this phenomena. So it always tells you something about the long lead times of these events, but more telling, I think the signal, as we will learn, is about an event that happened 1.3 billion years ago. At this time there wasn't even multicellular life on Earth, so we had a long lead time, and then actually I think the machine only came on 2 weeks before actually the signal was detected, so we're just in time. The format we'll have, you have 4 shorter presentations of a member of the School of Natural Sciences, which I would just introduce, and then we'll have a panel discussion, or actually even more, I think, a discussion with all of you, because this is indeed a topic that raises many questions, so the introductions will be short. We'll have in chronological order first Professor Matias Zaldarriaga, Professor in the School of Natural Sciences, of course an expert in cosmology, the microwave background, large-scale structure, dark matter, etc. Then we'll have a member, the John Bacall Fellow, Doron Kushnir, whose interest is also in high-energy astrophysics, supernova explosions, and many other fields. Then the Scott Tremaine, the Richard Black Professor in the School of Natural Science, will speak. And finally, we have Nadia Zakamska. She is based in Johns Hopkins. She has been a member here for a long time, a 5-year member. And she's now back as a member. In fact, she's the Deborah Lunder and Alan Zekowicz Founders Circles member. So we are among friends. It's very happy that this topic is discussed at the Institute again, since there's such a long tradition of studying gravity and all its aspects. Very appropriate, and I hope we'll learn more, and we'll learn also more about the kind of inspiring, energizing prospects for this field, because I think one thing we are celebrating here is not only the conclusion of a long, long effort, but perhaps more important, the begin, as many said, a new great era in physics and astrophysics. So with no more words, I want to give the word to you, Matias.
Oh, great. Thanks very much, Robert, for inviting us to put this thing together. Last week, the scientists from the LIGO collaboration, the Laser Interferometer Gravitational-Wave Observatory, made an astonishing announcement. They said they had observed gravitational waves which had been produced by 2 black holes inspiraling one another very fast, many times per second, almost as fast as the speed of light. They collided, they formed another black hole, they emitted gravitational waves. That happened 1 billion years ago. Those gravitational waves traveled across the entire universe. Then they passed through the Earth. They just were turning on their new machine, and they detected it. And that was great. It was really something for us. The goal of today is to tell you a little bit about what happened and what we've learned from it, what are these sources that produce these gravitational waves, and what we might learn about this new way of doing astronomy using gravitational waves. So my particular objective in the next few minutes is to parse a little bit more that thing that I said very quickly about what exactly happened, okay? And then the other members of the panel will tell you about the sources for gravitational waves and also other things that we might expect for the future. So the first thing then is to talk about gravitational waves. What are gravitational waves? To talk about gravitational waves, I will start with some other form of waves that should be more familiar. The force of electricity and magnetism. So we are familiar with charges, positive, negative charges, charges of different sign. They attract each other. That's what holds together atoms and molecules and so on. When you wiggle those charges and you make them move around, they create a form of waves that can travel in empty space called electromagnetic waves, and they move away. And we're all familiar with those waves, very much familiar. We use them all the time. They have different names depending on how fast these charges are wiggled. They form what we call the electromagnetic spectrum, and we use this all the time. So from the most important, perhaps, of these forms of radiation, visible light. So that's just what light is. So charges are being moved around. They create this radiation, and our eyes are especially set up to detect light of some particular period. But we use light or electromagnetic radiation of all different wavelengths all the time, from radios to the microwave oven to for changing the channel in the TV, the remote control, visible light, UV radiation, X-rays when we go to the dentist or other kind of doctor, etc. So these are then what all these have in common. These are charges. To produce the radiation, you have to wiggle around charges. Let's take, for example, the case of a radio wave. So somebody talks, that generates waves in the air. Those are not waves that can travel in empty space. So the sound waves, they travel in the air by compressing the air. They get to the microphone, they wiggle around some magnet in the microphone. That creates some current that is amplified and used to wiggle around some charges in the antenna. Those charges in the antenna wiggle around. They create these electromagnetic waves. They can travel in empty space. That's how we communicate with spacecraft outside of the Earth. And in the case of radio, they eventually get to your receiver. What happens when these electromagnetic waves get to encounter a charge? They produce an electric force that they wiggle around the charge, in this case in the antenna of the receiver. That is used then to move a speaker, or amplify, that signal is amplified, used to move a speaker, and the speaker creates sound waves that you can use, okay, that you can hear. So that's electromagnetic wave. We use them all the time. We're relatively familiar with them. So what about gravitational waves? So these are other form of waves that can also travel in empty space. So we are also familiar with the force of gravity. The force of gravity is very weak if we are talking about atoms and molecules. But by the time you talk about big objects like planets and stars that are not charged, electrically charged, but they have mass, this mass produces gravity. That's what makes things go around each other in the sky. And so just like in the case of electromagnetic radiation, when masses move around, they create this other form of waves that can also travel in empty space called gravitational waves. Both of these waves travel very fast at the speed of what we call the speed of light, 300,000 kilometers per second. And so in this particular case, two black holes very far away in a very distant galaxy, or it depends, maybe not so distant for today's standard, but in a distant galaxy, two black holes were spinning around. They emitted these gravitational waves. Think of that as the antenna of the case of the radio waves. And then so what happens then with electromagnetic waves? If they encounter a charge, they make it move, right? In the case of gravity, what creates gravity? Masses. Every mass creates gravity, and every mass experiences the force of gravity. So when a gravitational wave passes by, every mass is moved around, okay? So everything is moved around when a gravitational wave passes. So this gravitational wave passed through the Earth and wiggled everything around. Of course, not this much. But what did they actually, it's, as we will discuss later, much less than that, much less than that. And so what were the masses that they were tracking very carefully to see how they moved around? They were big mirrors, about 40 kilograms in mass, that they were hanging on some pendulums at the ends of these tunnels. Those are very long tunnels, which are in vacuum, so the air is taken out of them. And there are mirrors at the end of these long tunnels, and they monitor the separation of these mirrors by shining light through them. So that's where the laser comes in. So when this gravitational wave passed, it wiggled around these mirrors. And just like in the case of in the radio receiver, you use that signal, that the electric force that wiggles the charges, then you convert it somehow into sound to hear it. In this case, this wiggling of the mirror was sensed by these lasers and converted into light to be measured. Okay, but what did they actually see? So they actually have two of these antennas, two of these machines, one in Washington State and the other one in Louisiana. And what I'm showing there is on the x-axis is time, on the y-axis is a measurement of how the mirrors are moving with respect to one another, okay? And so what you see, so let's say that I will discuss a little bit more that strain means later, but for now, it's just the distance between the mirrors. So you can see in the top panel there, let's see, is this better? Yeah. So you can see the mirrors are wiggling around and going near, far, near, far, near, far, near, far. Things to notice, the amount of time that passed when the whole thing happened. This from here to here is a tenth of a second, 1/10 of 1 second. So this gravitational wave passed through pretty fast, okay? Now, the gravitational waves, as we were saying, they're supposed to travel at the speed of 300,000 kilometers per second. So they will arrive at one of the detectors first and then travel to the other one. That takes a few milliseconds from one to the other. And indeed, a few milliseconds later, they saw it in the second detector. And if you shift the two to account for that change in the time, the two lines lie on top of each other, okay? Other thing to note is thing goes up and down and up and down. This is just reflection of how fast these two masses are moving around. So each time they move around, in fact, every half the time they move around, it goes up and down in this curve. So boom, 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 boom. And the thing to notice is, first of all, they are going around pretty fast because in a small fraction of a second, this thing is going up and down and up and down. But also, you notice that the time it takes for it to go up and down, so these are the mirrors doing like that, is getting shorter and shorter, okay? And the amount by which the mirrors are going up and down is getting larger and larger. The signal is going up in time, okay? So what is happening is the following. You have these two very big black holes. They're orbiting one another and emitting these gravitational waves. As they do so, the system loses energy that is being taken away by the gravitational waves. When that happens, the orbit shrinks a little bit. The two masses get closer together, and when masses get closer together, they go around each other faster. And so this is losing more and more energy. They're going faster and faster and faster, and that's why you see this wiggling like that, until there comes the point when the two black holes meet each other. They form a big deformed black hole with a weird shape that then moves around and rings down, we call it, until it forms a final black hole, rotating black hole, and that's when the signal goes down, okay? Great, and in all of these panels, there's also a little curve, which is the calculation from the theory of gravity of what you would predict if two masses were doing the story that I just told you. You would predict that the mirrors should move like this curve is showing, and you can see that the data, which is the more jiggly line, lies on top of the calculation, okay? And this, including the part of the calculation, which is not so easy to do, which is when the two black holes merge and they have a weird shape and they start ringing down. That's a very challenging calculation to do. That it's only recently that people managed to do it. Another thing that I wanted to mention is that if you were to calculate how many times you have to go around until you merge, what does that depend upon? It depends upon how fast you're going. If you're going to merge in just a few orbits like you're seeing here, just a few times, you just see the last few times that they're going around and then they merge, you must be traveling close to the speed of light. If not, it takes a very, very long time to lose energy and emit gravitational waves. So just from the very fact that this is happening, we see the end of the thing. We know that during this period, the two things are traveling super fast, very close to the speed of light. And okay, well, it's shown in there, but let me just. So how do you make things go around so fast around each other, close to the speed of light? So as I was telling you, you have two masses orbiting one another. When they get closer, they go faster. But in order to go as fast as the speed of light, they really need to get very close to each other. So for example, if you're talking about something of the size of the sun, of the mass of the sun, sorry, and if you want to make things orbiting it go as fast as the speed of light, you really need to make it very, very small, of size not a million of kilometers like the sun, but more like 10 kilometers. So you really need to squeeze the whole sun into something of the size of a city, right? So what we are seeing in this event is two things that are very, very compact, moving very fast, merging together into one, okay? It's good that the universe even produces these kind of objects, that they are out there. So, and Doron will tell you a little bit more about what we knew and what we know now about how these kind of objects, and whether these objects are also put together in pairs, in binary orbits, and that they're moving fast enough that they would lose enough gravitational waves to merge and that we can detect. So let me finish by noting a few things about the signal again. So talking about the signal again. So again, going up and down, up and down, up and down. The first thing that I already said, but I want to repeat, is the fact that the shape of this signal is just as you can calculate for two black holes that merge using the theory of gravity, which is quite remarkable. We had tested this formula of how gravitational waves, the amount of gravitational waves that a system of two masses going around produces before, but the two masses were two neutron stars moving at 1,000th of the speed of light. Now we are talking about testing this when the two things are moving almost at the speed of light, when we're talking also about black holes, that they merge, they form this weird shaped black hole that rings down and eventually ends up with a spinning black hole. So it's a completely different level of test of these equations. And also from the very details of this curve, the people have been able to infer that the two things that were coming were actually two black holes, what their masses were, some information about how fast they were spinning, and then also about the black hole that formed in the end, how much mass it had, how fast it was spinning. All of that based on this little wiggle that lasted a small fraction of a second, okay? So that's, I think, was pretty remarkable. So a few more properties about this event. So if you go at the paper and look at the table, you will see that the idea is that there was two black holes, one of 36 solar masses, more or less, one of 29 solar masses. If you add these two numbers up, you get 65 solar masses. But the final black hole at the end was 62 solar masses. What happened with the three solar masses that are missing? Okay? So that is what provided the energy for these gravitational waves that left. So so using the formula energy equals mass times c squared, which is a familiar formula in t-shirts. So using that formula, you can calculate how much energy was produced. So three entire suns vanished in a small fraction of a second, producing this burst of gravitational waves. That's not just the amount of energy is, of course, a lot, but also it happened incredibly fast. In fact, I think it's happening at as fast as we can imagine things, almost as fast as we can imagine things happening in our universe. You would see in the news report, so if you take that, the total amount of energy, you divide it by this small fraction of a second where all this energy came out, you get a lot of energy coming out per second, equivalent to all the energy being put in light by 10 to the 23 stars like the sun. This is more than all the stars in the universe, okay? I mean, they are putting it in the form of light. These are gravitational waves. But just to get a sense of it, during this brief 0.1 second of time, this thing outshine all the stars in the entire universe, okay? Not in light, but in gravitational waves, okay? But as I was saying, this is as much energy as we think, almost as much energy as you think can be moved around. Why is that? Imagine that you wanted to create a huge explosion and liberate it as fast as you can. What do you want to do? You want to take all the mass that you can and convert it, say, into light. So you take all the mass and you use the formula mc squared. That's all the energy that you have. And this light is moving as fast as it possibly can, so at the speed of light. So if you want this to happen fast and to escape this region as fast as possible, you need to want to make this region as small as you can, because the smaller the region, the less it will take light to escape the region, okay? So what you want to do is take all the mass, convert it into light, but making the region as smaller as you possibly can. But you know, as you make the region smaller and smaller and smaller, in order to escape, you need to go faster and faster and faster because of the force of gravity. Until eventually, if you make it too small, you make a black hole and nothing can escape. So if you want to have this explosion, you better stop at the moment close to the black hole, because if not, nothing will be able to escape. So if you take all that energy, you put it in the size of a black hole, and you calculate how much energy you can come out the fastest possible, you get a formula that just involves the Newton's constant and the speed of light. And this is most things in the universe are produced much less than this in energy per unit time, because things cannot escape as fast from the places, because these explosions are filled with matter, things cannot escape. So getting to here, this is just the maximum we think from just general relativity, simple principles. It's usually not achievable, but this is a system that is the closest you can imagine to achieving it, and it comes pretty close to it. It's like perhaps 0.1% of these. So this is a tremendously violent thing that happened in our universe, and most probably it's happening all the time, right? Because they happen to catch one. And so the final thing that I wanted to mention is about the size of the effect. That this is something that so far I did in the detector I didn't say so far. This number that was quoted there, strain 10 to the minus 21. What is this strain? Okay, so as I was saying, when the gravitational wave passes, it creates forces, so it moves things around. So if you want to calculate how much two things that were separated by some distance move, okay, how much do they move? So what you need to do is to take the distance, the original distance that the two things were, and multiply that by this strain, 10 to the minus 21. So I wrote down 10 to the minus 21 out so that you can see. So it's 0.0000000, and the 21 plays a 1. So if you want to know by how much these mirrors were moving, you need to multiply 4 kilometers, the distance between these two mirrors, and multiply by 0.001. Okay, you will get a very small number. How small a number? Even less than the size of the proton inside of the nucleus of an atom. Okay, so this is a minuscule distance. Okay, so the two things that you immediately, when you are faced with this, you would ask is, why is the signal so small? Why is it so small? And the other one, how can they possibly have done this, right? And so simple, just to get a sense as to why the signal is so small, the size of these gravitational waves is basically, so waves, as they travel out, their amplitude, their size decreases. And we are familiar with this. If we want to talk to somebody, if we go further and further away, you know, we have to shout. It's more difficult because the size of the signal is going up. Or light, if we turn a flashlight, if we go very far, nobody can see us, right? We need to build a telescope, binoculars, or something like that. So, so the waves its amplitudes are going down, and the amplitude goes down inversely proportional to the distance. If you go twice as far, the size is twice as small, and so on. So what is the size of this? It's basically the distance to what is the size of this strain? How can you calculate the size, this 10 to the minus 21? This is basically the size of the object that was producing these gravitational waves, which is, I didn't say, I think these black holes were like at the end, the big one, 200 kilometers, something like that. You have to take the distance to that object, how many times you can fit 200 kilometers in there. So Of course, this is happening in a faraway galaxy, 400 megaparsecs away. A megaparsec is roughly the distance to our nearest neighbor, Andromeda galaxy, right? So this is happening at an astronomical distance, very far away. And the size of this signal is just given by taking dividing the 400 or the 100 kilometers divided by this very large distance. And that's how many of these black holes, if you want, if you put a ruler of 200 kilometers between us and then how many of these rulers do you actually need, okay? And so how did they manage to do this? Okay, so let me just say quickly, you should think of this perhaps as a timing experiment. So what they were doing is shining light. They had really two arms. Light came to some called beam splitter and went in one direction or the other. And they were timing how much time light took to go in this direction compared to when it went in this other direction. When the gravitational wave passes, it changes these two sides. And what happens is that, if the two sides were exactly the same, all the light that went from this laser to this and to the two sides would come out into the laser. If there's a mismatch in the two sides, a little bit of the light there's a certain probability that some of the light will not go back into the laser, but will go to what they're calling this photodetector, their camera. The probability for this to happen, you can calculate by dividing the change in the distance given by the light travel time, divided by the wavelength of the light. And the light, this laser that they were using, had a wavelength of only 1,000 microns. So that gives you already, and furthermore, light was not really traveling 4 kilometers. It was really traveling more like 1,600 kilometers because there were two mirrors here and they were bouncing back and forth back. So before the light could escape back, it had really traveled 1,600 kilometers, not 4 kilometers. So they keep adding this kind of improvements. From there you get a 10 to the 12. Then you have to know how many of these photons, how many, you're doing this timing experiment. You have this particle of light called photons. You have the certain probability that the photon, because of this mismatch, will end up in this direction. In order to measure such a small probability, you need to have a lot of photons going around. And indeed, they had a lot of photons. They have a very powerful laser. 700 watts of power were incident in there. That's something like 10 to the 21 photons of this laser every second. So you need to take the square root of this number, and by accumulating these very big factors is that they measure this very little distance. So I know I went very fast, but I just wanted to at least tell you that this is not only a spectacular event from the point of view of what happened in the universe, it's also a spectacular event for what kind of thing people are able to measure. And of course, anything that I also should say, anything that moves these mirrors that is not the gravitational waves, it's a problem. So they have super sophisticated isolation systems to keep these mirrors from not moving around because of all of the trucks going by, little earthquake, waves, all of this stuff is a problem. So they have to kill those vibrations by almost 10 orders of magnitude. So it's a remarkable feat of engineering, I think. And so I'll stop here, and what I think what we'll do next is tell you a little bit about the sources and also about other ways to measure these gravitational waves. Just as in the case of electromagnetic wave, there are we talk about radio waves and waves of different frequencies. So is the case in gravitational waves, and there's a bunch of experiments also trying to that will try to see gravitational waves with other frequencies. The only one so far that has seen something is this ground-based experiments LIGO. That's the big news. But the astronomical community has been working on other types of ways to measure gravitational waves of different periods for a long time. And so a little bit we will tell you about that. Okay, so let me stop there and go on.
All right, so I will try to describe a little bit about the sources that actually produce this gravitational wave. So let me see. All right. So as Matias explained, we need two things in order to produce these gravitational waves. We need to accelerate a lot of mass, and we need to accelerate to the speed of light. Now, doing this on Earth is just impossible, so we must go to astrophysical sources. And I think the simplest astrophysical source that we can think about is a binary star, a binary system, where you have two objects orbiting each other, emitting these gravitational waves. So what are the requirements from this binary system that it will be detected on Earth? So the first of all, we need to move a lot of mass. What is a lot of mass? So I'm using this m target, which is m sun. So we need roughly the mass of the sun to be moving away. The second thing, we need when they orbit each other and they merge, at some point they will hit each other. When they hit each other, that's it. There are no more waves. So we want them to hit each other only after they reach to the speed of light. An equivalent way is when they hit each other, the relative velocity is just the escape velocity from each star. So what we want is that the escape velocity will be close to the speed of light. It's another requirement from this object. And the last thing, as Matias explained, this is an antenna which have some typical size. LIGO is an antenna that will going to detect these waves at some typical size. If we want the two frequencies to match, we need the size of the system to be comparable to the size of the detector, which is LIGO. So LIGO is like 10 kilometers. This is what we require from the system. Of course, this is not the way it was planned. People were planning LIGO to be 10 kilometers because of some consideration, but this is the basic thing. So imagine that we are at September 13, 2015, and excuse me for being confused and using my European tradition of dates. So it's day, month, year, and we just want to see what is there in the universe that can actually make these gravitational waves. So this is one day before the detection of LIGO, okay? So let's just see what we know that exists in the universe. So obviously we know about planets. The problem, they are not massive enough. They are way too big. And the escape velocity is too small. So what is the escape velocity? Imagine you have some spaceship, and you have to give it some velocity to escape Earth. So what is the velocity you have to give it? It's 10 kilometers per second, which is pretty fast. Just to get a sense, what is a kilometer per second? Imagine that in 1 second, you are in Princeton University. Right? This is very fast. So 10 kilometers per second is even faster, but still it's tiny compared to the speed of light. So this is good for us because we can go to the moon or escape Earth if something happened, but this is very unfortunate for gravitational waves. So this is irrelevant for gravitational waves. How about just stars? They can be pretty massive, maybe 100 solar masses. The problem, they are way too big for LIGO, and the escape velocity is still too small. Now, stars, when they finish burning the fuel, they collapse. And when they collapse, they can stop at a smaller configuration, which we call a white dwarf. So the size of white dwarf is similar to the size of Earth. The mass is good. It's like 1 solar mass. This is very good. The size is too big. And also, the escape velocity is too small, only 1% of the speed of light. But by the way, this is not very bad. So in principle, if you can build a larger detector, we might be able to detect these guys. But for LIGO, this is just irrelevant. Now, the mass of this object cannot be much larger than 1.5 solar mass. It means that if the original star was heavier, it will continue to collapse until it will stop at a smaller configuration, which we call a neutron star. Now, the mass of this neutron star is once again a few solar mass. This is very good. The size is 10 kilometers, which is perfect. It's just the size of LIGO. And the escape velocity is very close to the speed of light. So neutron stars are perfect target for LIGO. This is, of course, was well known. This is why LIGO is 10 kilometers. But then it's not enough. We need the system to be in binaries, which will merge. So we go to our inventory and we ask how many double neutron star systems we know of. And the answer is 13. So this is pretty good. It's much larger than 0. But this is not enough because we want them to merge very fast. Otherwise, we won't detect them. So how many systems will merge fast enough, what we will call within the edge of the universe, but the meaning is really fast enough? 6. So this is good. But there is a caveat. we are not completely sure that all of these systems are really double Newton stars. So how many systems we are completely sure are double Newton star? And the answer is 1. But it will merge fast enough. Now, it may look like small numbers, but actually it's pretty good. And Stelfini at 1991 was able to use this to estimate. OK, so the problem is, of course, if you just wait for this system to merge, we can wait for a very long time. But if we can observe a very large volume of the universe, then we can detect a lot of these systems, and maybe one of them will just merge during the time of the observation. So you can calculate what is the required sensitivity from the detector to detect large enough volume to actually see the system. This is the calculation it did. And when LIGO will reach its final goal, which they are still not there, they're still improving the detector, then it will be able to detect a few events per year. Now, the contribution of the Institute for Advanced Study for this paper is in the acknowledgement of the paper, where Stel said this would not have been written up if John Bacall had accepted the bet and Kip Thorne had not negged and encouraged. And John Bacall is the founder of the astrophysics department here. So it's a small contribution, but nevertheless. OK, these are good targets. What happens if the mass is even larger than free solar mass? It will continue to collapse. It will make a black hole. Now, the mass of black holes are unlimited. This is very good. If there are a few solar mass, the radius is 10 kilometers. This is LIGO size. And the escape velocity is exactly the speed of light. This is why they call them black holes. So we go back to our inventory, and we check how many double black hole systems we know of. And the answer is very simple, 0. Now, this is for September 13, right, before the detection. OK, here's another possibility. How about a Newton star and a black hole? This can also work. How many systems do we know of? 0. So what do? We need to calculate the sensitivity, the volume, and such. And the answer is very simple. There's nothing we can do. So what is the strategy of LIGO as before the detection? Let's build a detector which will be able to detect double Newton stars. And this is how this detector was planned. But in the meantime, we are keep improving the detector all the time. Let's look for other signals as well. And let's hope for the best. And lucky for all of us, at September 14, 2015, they actually detected a merger of a pair of black holes. So now what we need to do is to update our inventory list of the universe. So at the beginning, we know of nothing, right? But at 74, the first double Newton star system has been discovered, and it's a fast merging system. One day before the discovery, there were 30 known double Newton star systems. 6 of them will merge fast. At September 14, at 9:50 a.m., 45 seconds, there is one system that we know of. The only problem, after 1 second it merged, so we go back to 0. But, of course, this is a joke. This is a serious discovery. LIGO discovered a new type of system in the universe. These things happen very rarely in history. In the whole history of human race, it's only been discovered a few times. So this is really an historical moment. So besides the fact that this system exists, what can we learn from this? We can learn a lot. Just to demonstrate how ignorant we are about the system, this is a paper from some people from the LIGO collaboration, some not. Farr et al. 2012, only 3 years ago. And they have different models for how many events of black hole merger will be detected and at which masses the black holes are going to be. This is this x-axis. The mass, they call it the chirp mass, but this is basically the average mass of the system. And you see 4 different models, large variation, we don't know anything. And the actual LIGO detection was here. So completely outside of any model. So we were truly ignorant. And this detection will teach us a lot about these systems. So what should we expect in the near future from LIGO? So LIGO is continue to be upgraded, continue to collect data. More and more systems are being observed. Obviously, we will detect many more black hole systems. This will allow us to have an accurate measurement of the population of these systems. And we may get some clues for how these systems formed and where did they came from. When LIGO is completed, we should detect a few neutron star mergers. And if we're lucky, maybe we'll detect even neutron star black hole. But let me give you just one note of caution. The first double neutron star system was detected 40 years ago, and we are still not completely sure where this system came from. So it's not clear that even if you measure a lot of this black hole system, we'll actually gain something. So the one thing that we really should do now is to think. Okay, thank you.
Over the next few months and years is the detection of many more really interesting systems from LIGO. I want to look further into the future, and I want to do so by starting with this sort of messy-looking diagram, which basically tells you what the sensitivity of LIGO is. This axis is the strain that Matias told you about, ranging from 1 part in 10 to the 16 to 1 part in 10 to the 23rd. These are a set of curves going to smaller, lower and lower sensitivity as a function of frequency. And what you can, this is the current status of LIGO. And what you can see is that the sensitivity has it's pretty sensitive over a broad range of frequencies from about 100 to 1,000 hertz, but the sensitivity gets extremely bad extremely rapidly at around 20 hertz. Actually, in some ways, this is similar to what happens with the human ear. A healthy young person can hear down to about the same frequency as LIGO, down to about 20 hertz. The reason for this drop-off in sensitivity is basically twofold. The first is that there's a limit to the size of the arms of the interferometer, and you can't detect a frequency that's slower than the time it takes light to go back and forth inside the system. The second reason is seismic noise. LIGO is extremely well insulated from the minor tremors that you get from small earthquakes throughout the world. The trouble is that in the interior of the Earth, the seismic waves from these earthquakes are propagating through, causing periodic changes in the density of the Earth, and those are generating, if you like, gravitational waves that are ruining the sensitivity of LIGO to the astrophysical gravitational waves. The trouble with this cutoff in sensitivity is that most of the interesting gravitational wave sources are at much lower frequencies. Over here, somewhere between a hertz and a microhertz, that is periods of somewhere between a few seconds and a few days. The only way to avoid those problems is to go into space, and the current proposal to build a space-based gravitational wave detector is called ELISA, for either the Evolved or European Laser Interferometer Space Antenna. It's similar to LIGO in concept. It involves an interferometer with 2 arms with light bouncing back and forth between the arms of the interferometer. I should just mention parenthetically that one of the reasons that physicists think Einstein is so wonderful is that not only did he invent general relativity, but he also made the conceptual advance that eventually, decades later, led to the concept of lasers. So the idea is that to get around the limitations of seismic noise and to get around the limitation on arm width, you put up a constellation of 3 spacecraft orbiting around the sun in an orbit that trails behind the Earth. You set up lasers to communicate between these spacecraft in pairs, and then you measure very carefully the distance between the spacecraft and look for changes in the distance caused by gravitational waves. This contains 2 really radical and remarkable technological concepts. The first is the idea of a test mass. The difficulty with making measurements with spacecraft is that they're constantly being buffeted by micrometeorites, by the solar wind and so forth. And that creates a noise of itself that obscures the gravitational radiation that you're looking for. So inside each spacecraft, there'll be a small mass called a test mass surrounded by the spacecraft in a cavity. And the idea is that as that test mass moves in response to gravity, the spacecraft will very delicately sense where it's going and move the spacecraft around it so that it stays away from the walls of its container. And that means that the test mass is immune to all the effects that are hitting the spacecraft from the outside and feels only the gravitational waves. So this is a remarkable technical achievement. The expectation is that they can measure the distances between the spacecraft to 1/1000th of a centimeter, despite the fact that the length of the arms of the interferometer is about 1,000,000 kilometers. It should be sensitive to frequencies in the range out to periods of a few hours, which is enough to get a lot of the most interesting sources. This project has been being developed for a long time, since the 1990s. It was originally a joint European-US project, but the US pulled out 4 or 5 years ago because of budget problems in NASA. Currently, the projected launch date is 2034. That sounds an awfully long way away, but I want to stress that distance is not because of the technical difficulties in making the spacecraft work. It's solely a result of budgetary limitations. It's gotten into the queue for major missions for the European Space Agency, and that's when it's going to get to the head of the queue. As I said, the concept contains two very challenging technologies. First being these 1,000,000-kilometer-long interferometers. The second being the freely floating test masses. But this is not science fiction. Last December, the European Space Agency launched a mission called LISA Pathfinder, which is designed specifically to check out whether they can make these test masses float freely within a cavity within the spacecraft. Obviously, the problem is that when you launch it, you have to hold the test mass in place and then only release it after the spacecraft is safely launched and freely floating through space. As I said, LISA Pathfinder was launched in December. Just last week, they released the test masses. They're still holding the test masses in place with small gas jets. But next Tuesday, the plan is that they're going to turn off the gas jets and try to, so that instead of the position of the test masses being controlled by the spacecraft, the position of the test mass will control the spacecraft. If that test is successful next week, that will be, I think, one of the really major technical hurdles that will have been surmounted to make LISA possible. This again is the diagram of the sensitivity to strain versus frequency. This is a variety of ground-based detectors with the current version, advanced LIGO, showing a curve like this. The event that was announced last week is here, comfortably above the LIGO sensitivity. And this is, for comparison, what LISA will be able to do. Not as sensitive to strains, but much more important, sensitive to much lower frequencies. There's a huge variety of sources that LISA should be able to see. Not only will it be able to see a huge variety of sources, but it'll give, we hope, a much cleaner signal than LIGO. The critical number is the signal-to-noise ratio. Last week's event, which you see here, had a signal-to-noise of about 20. It still looks pretty clean. But LISA, for example, will detect gravitational waves from 50 or so known nearby binary stars with a signal-to-noise ratio exceeding 50. It'll detect thousands of other binary stars and every binary star in the galaxy with an orbit of less than 30 minutes. These are precisely the systems that Doron said we didn't know enough about. Most remarkably, it should detect mergers of what are called supermassive binary black holes. These are similar, except for scale, to the one in the event that LIGO saw last week, but the difference in scale is remarkable. Instead of a few tens of solar masses, these are up to 1 billion solar masses. Their mergers are the most energetic events in the universe. LISA will be able to see them out to the edge of the universe, and there's some hope that it will detect some of the signal-to-noise as large as 1,000. With a signal-to-noise that high, you can produce exquisite tests of the most extreme predictions of general relativity in the limits where velocities are close to the speed of light. Those are tests that can't be conducted in any other way. It may also shed light on cosmology by perhaps detecting gravitational waves that were produced in the tiny fraction of a second right after the Big Bang. It's an extraordinarily exciting project. I'm exercising every day to make sure I live long enough to see it launch. In the near term, there are other options for detecting waves, and Nadia will tell us about those.
All right, I am going to switch gears a little bit. You have heard from Matias and from Scott about these incredible high precision human-built machines to detect gravitational waves. Astronomers have been very clever, and they have been trying to use astronomical sources to do this high precision measurement for us instead of building these observatories on the ground and in space. So what I'm going to be talking about is so-called pulsar timing and pulsar timing array. So let's start with talking about what pulsars are. Pulsars are rotating neutron stars. You have already heard a lot about neutron stars from Doron. They have, if you will, hot spot, which produces a beam of radio emission, which is inclined relative to the axis of rotation of the star. And so as the star rotates, if the observer happens to be fortuitously positioned within the beam will sweep past the Earth in the effect similar to a lighthouse, rotating and sweeping past the observer. And so the observer will see brief flashes of radio emission, pulses. This animation is actually too slow by a factor of about 1,000. The fastest known are producing hundreds of pulses per second. So what this is a very precise clock. And those pulsars are distributed in our galaxy over a large range of scales. And so those are these very precise clocks through which the gravitational wave passes, producing distortions in the space-time through which the signals must propagate. Pulsars have already done an enormous amount for gravitational wave astronomy. I think both Matias and Doron have already mentioned that. They provided the first direct evidence for the existence of gravitational waves all the way back in 1975. This is a system, the first such system discovered is called Halson-Taylor pulsar, and they received the Nobel Prize in Physics in 1993 for this discovery. It's a pulsar, so with this beam of light flashing past the observer in a binary system with another neutron star, which is passive, so we don't see it as a pulsar. More recently, there was another spectacular discovery with two neutron stars in an orbit around each other that are both active as pulsars at the same time. So you get even more observations from a system like that. So what is happening, as has already been mentioned before, that as the two massive objects rotate around one another on this orbit, they're losing energy to gravitational wave emission. So the orbit is shrinking. They are rotating faster and faster and faster. On this graph, you're looking at the real data for monitoring of the system, the Halson-Taylor pulsar, all the way from the discovery 1975 to roughly present day. And this is a measure of the shrinkage of the orbit. And this solid line over here is the prediction of the general relativity. And those points are the data points, and they are actually bigger than the measurement uncertainties on those points. So it's a spectacular success of general relativity in predicting what these systems are going to do as a function of time. And so as the orbit shrinks and shrinks, we know that it will merge. It's going to take a number of dozens of millions of years in this particular case. So the agreement in both of those systems, there have been a number of extremely precise measurements, and the agreement with the predictions of general relativity is spectacular, within 0.1%. Okay, so this is neutron stars as sources of gravitational waves. So now let me go back to the possibility of using those things as detectors of gravitational waves. And so I'm going to describe something called International Pulsar Timing Array. I think this is a slide that's already been shown, but let me walk you through this one more time. So both the pulsar timing array and the space interferometer that Scott was talking about are most sensitive to the supermassive black hole binaries. The black holes in the centers of galaxies, if two galaxies merge, the two black holes find themselves in the center of a newly formed galaxy, rotate around one another. This is in contrast to the LIGO event that happened last week, which measured the merger of the stellar mass black hole binary. The difference between the pulsar timing array and the space-based interferometer is in this frequency sensitivity. So the space-based interferometer is more sensitive to the final stage of the supermassive black hole merger, whereas the pulsar timing array is sensitive to the first phase when the two supermassive black holes in the binary slowly losing energy to the gravitational waves, so the first in-spiral phase. So this is not science fiction. This is already going on. There are over a dozen radio telescopes around the world that are actively monitoring a network of pulsars, which are these precise clocks. And about 50 pulsars are being monitored right now, and more systems are being added as more systems are discovered. This has been working close to about a dozen years, with some of the older systems have been monitored for over 20 years. So again, this is sensitive to supermassive binary black line spirals, but this is somewhat different from the previous events from the events you heard about previously. So instead of being sensitive to an individual binary black hole somewhere nearby, this array is much more likely to detect the so-called stochastic background. So sum up all of the faint signals from all of the binary supermassive black holes in the universe, sum that up, and that produces a sort of gravitational wave noise. All right, so this is what the pulsar timing array is most likely sensitive to. This is one particular prediction of gravitational wave background from one of the recent papers. As a function of the frequency of the gravitational waves, and this is the strain, so the measure of how strong the gravitational wave is. The International Pulsar Timing Array has been working on for close to 10 years. They just released their papers within the last year, including one on February 11th for the obvious reasons. And this is their current upper limit. All right, so what are those shaded regions? So some scientists in this paper put together everything we know about the population of supermassive black holes and made predictions as to what we should expect for the population of binary supermassive black holes. And the black regions and the darker gray regions are their most likely predictions for what the stochastic background of gravitational waves should look like. The pulsar timing array has reported a non-detection, which is smack in the middle of these predictions, and in fact is ruling out a lot of these models. And so you can look at it in two ways. You can say these timing arrays are becoming more and more sensitive, so we might detect something any day now. So with a caveat that it's really not one event that they're going to be sensitive to. It's more like a statistical detection in which they're trying to pull this combination of these signals from the background noise of their data. So it's much more likely that it's going to be another year or two if the stochastic background of gravitational waves does exist. A more pessimistic view of things is that the stochastic gravitational background doesn't exist. Why would that be the case? Well, perhaps supermassive black hole binaries stall at some distance where they're very inefficient gravitational wave emitters, and so they never even get down to get down to the orbital separations where they can merge quickly enough, or instead they might merge very quickly because of non-gravitational events. Non-gravitational physics, such as interactions with surrounding gas, and so on. This is a rapidly improving field. There will be a lot of technological advances over the next few years, which will allow the pulsar timing arrays to push their sensitivity down by at least another factor of 10. At that point, if nothing is seen, this is going to be very, very telling. But this upper limit that already exists today is already pretty interesting. And so with that, I think I'll finish, and we will open for questions.
Undoubtedly, many, many questions. And before, I think I want to turn to the audience and perhaps collect some group of questions. I want to ask two things. Scott, you mentioned the long lead term in terms of these projects. I want just to ask, can you say something about the time it took to set up this whole operation LIGO? How did we get to this moment of detection? When did it start? And what's in some sense what was necessary to reach this great success?
Well, I perhaps the best way to indicate how long it took is that in 2001, I had a very nice glass of wine from offered to me by one of my colleagues, who bet one of the principal advocates for LIGO on whether gravitational waves would be detected before the year 2000. Already,
When did you make that bet?
I think it wasn't me. I wish I had, but I think the bet was made early in the 1990s. So this gives at least some indication of how long a road it's been. So it's taken well over 2 decades. It's cost well over $1 billion. And although that sounds pretty daunting, I mean, I think we have to give credit to the National Science Foundation, which is supposed to invest in risky long lead research and consistently supported the LIGO collaboration for well over 2 decades. It's their largest experimental project they've ever supported, and they did that for a very long time with no results, and I think they've been vindicated.
It was very good to see that they played a major role with the press announcement. Matias, I want to do, because we have been talking about gravitational waves in the last few years. There was at some point rumor of a detection of primordial gravitational waves. That raised many questions at that point, how solid was the result. Can you say something about the solidity of this result vis-a-vis what happened 2 years ago?
Well, I just hope that it's not a repetition of what happened.
For all of you, that was a detection that had to be retracted, right?
Exactly. So some time ago, we've been talking so far about gravitational waves that are produced by rotating objects, stars or supermassive black holes. So far, those were the ones that were detected by LIGO. There's also the chance that the gravitational waves were produced in the very early universe, before the hot part of the Big Bang. Those gravitational waves will leave signatures in something called the cosmic microwave background, and would be an indication of what happened in the very, very earliest phases of the history of the universe. And there was a claimed detection of that by a telescope called BICEP on the South Pole, measuring this cosmic microwave background. And unfortunately, that had to be retracted. So I hope this is not the case here. I think this looks much more solid, but you know.
There are
never
some
know.
differences, right? This is peer-reviewed. This was two different collaborators. I think in some sense there was great care being taken before the result was announced. I'm agree.
I think it's true that this was peer review, and I hope much more care was taken before the results were announced. I don't particularly think that the peer review is the reason why we should believe or not believe this result, but I guess it's a plus that other people have looked at this announcement before, independent from the group that is making it, before the announcement is made. But I think in some sense, the other example of the gravitational waves from the Big Bang, the peer review happened in the open. The moment this was announced, we all went to try to check it in our various ways, and very quickly we understood, various people understood that there were some potential problems. So it's the peer review did work, but just in the open. And perhaps it's another way of doing it, and perhaps it's better.
Nadia, I was wondering, many people probably ask, if you were kind of just, certainly, astrophysicists working right now, somehow this announcement, did it kind of change your life? I mean, does it change the work of people? I mean, is there a dramatic change in terms of outlook, the kind of things you will be thinking about, etc.? Or in some sense, everybody just continues their own research program?
So this is a subject of some discussions that we've had over the last a couple of weeks here in our astrophysics group. There is definitely an astrophysical surprise to this discovery, which is that the masses of the two black holes that merged, 30 plus 30, maybe some other people completely anticipated that, but it was a complete surprise to me. I work in observational astronomy. We were not aware of the existence of objects of this mass. So not only, as Doron said,
because there was no way to measure them otherwise, right?
There is a way to measure there is a way to measure black hole masses of the black holes in our galaxy, but they're not in black hole binaries. And there are a couple of dozen of those sources known in our galaxy, and we're capable of measuring their masses, and they're all under 15 solar masses. And so not only the surprise was, as Doron explained, this is the first known black hole binary, but also the masses of those objects are very surprising. So in terms of observational astronomy, it is. I think it's going to initiate a lot of exploration of this area of the evolution of massive stars and how we can obtain objects of this mass in the first place.
Doron, you want to say something about it? You indicated we have only one. In fact, we have 0 now because it disappeared. That's a good point, actually. But we were lucky for 10 milliseconds. Of course, this also was a measurement done at the very beginning. I understood. You mean it was still in the test run of the detection. So the experiment has been going on for another 4 months. I know there were lots of rumors circling here. Is there anything you want to share with us? What are your expectations? I mean, honestly, in the next few months, will we be reading in the newspaper about new discoveries? What's in some sense your feeling?
So right now LIGO is not taking data. It's closed for another upgrade, and they will only open it again at the summer. But they have collected data for 4 months, and this discovery that was presented here was from the first month. So there's 4 times more data, and because of some rumors and so on, there are more detections, still not published, but I think it's kind of obvious that there are more detections from a very simple consideration. Just this signal event that was detected is very, very strong. And since we're measuring a large volume, there should be many others, weaker events, maybe a little bit more distance, maybe smaller masses, and so on. So it's very likely that there are more events and there are similar systems. And I think even this, so this used to be a science run, but now it's called an observational run. So even this first observational run will provide us with information about this black hole, their spins, their masses, and so on.
So these numbers will grow fast. That's what you think.
These numbers will grow fast, and they will they will give some constraints for models, for evolution, and so on.
I just actually want to turn to the audience, and if you allow me, I want to take a few questions and perhaps group them together. So there will be a mic, so just, yes, you. State it briefly.
So the first speaker had the chart where the gravity waves were illustrated. That was two black holes, approximately 30 solar masses each, which merged. Is that correct? Approximately 30
yes.
Solar mass, and then so they no longer. It's no longer a binary black hole. So, and one of the other speakers said that we know of no binary black hole systems in our universe. So the purpose, in other words, we don't know of any, but there was one that we think that we observed, so, but it no longer is. Obviously, if they merge, then it's no longer a binary. Am I correct on, is that what we're seeing here, basically?
I think that is an easy question.
Basically,
The answer is yes.
Yeah, I just want to make sure I understood what
Yes,
was
here in the
said.
front. Yes.
For the first speaker, you showed an overlay of the two different detectors in the two different states, and they were just phase shifted by a small amount of time, but it seemed like the amplitude was a little bit different. Shouldn't the amplitude be the exact same, just phase shifted over?
I think in this particular case, the amplitude should be similar. It's because the amplitude of the signal depends on the orientation of the detectors relative to the orientation of the plane of the orbit, and both detectors are oriented pretty similar to one another, and so that's why the amplitudes were similar, but not exactly the same. But one thing that we should say is that there are other detectors being built. There's one that will also come online it's built in Italy, and when more detectors come in, from the difference in amplitudes of these waves and arrival time in the different detectors, you will be able to pinpoint better where in the sky this signal is coming from, and that will be very useful to try to monitor these locations with other telescopes working with just the electromagnetic radiation to see if there's any kind of counterpart. In fact, there was even a claimed counterpart in the gamma rays for this event. We don't expect for black hole mergers to be such a thing, so if it were to be true, that would be a big surprise as well. So there will be a lot of work in that.
Nadia, you want to add to that?
Yeah, I would like to elaborate on the first question about the relationship between the event that was detected and what we did and did not know about such black holes before the event was detected. So suppose you have this 30 solar mass black hole binary in rotation, in orbital rotation. There is no way to find out about its existence via optical or infrared or radio or X-ray emission. We are completely blind to events like that in ordinary electromagnetic radiation. That is why we do not know of other systems like this. So this is exactly the illustration of how the gravitational wave detection provides a completely new way of observing the universe. This system would not be visible in electromagnetic radiation.
Do any of you want to say something about the prospects? Indeed, when we can kind of pinpoint these locations, what happens if you start to overlay electromagnetic and gravitational observations? What are kind of the promises there in kind of combining? Doron, you want to say something?
Sure. Yeah. Okay. The first thing to realize that it's very hard to get the position on the sky of these events. So we are used to accuracies which are roughly the wavelength of the emission divided by the size of the telescope. So if you think of degrees, we can do a tiny fraction of a degree. And this is the typical accuracies that we are used to. In gravitational wave, this is not the case. Right now, the localization is not far from the whole sky. But even when everything will be built in different locations on Earth and so on, we don't expect much better than, let's say, 1 degree. Now, 1 degree, it's a huge thing. 1 degree, there are many, many galaxies. and you need a lot of telescope time to actually go 1 degree and search for the thing. So it's going to be a very difficult thing to do, even in the future. But if you are lucky and by chance we do it, this will have a tremendous effect.
What would be the astrophysical candidates, which would be lighter both in gravity and in the visible
so
light?
I think
or
the most discussed option is two neutron stars, which merge, which people think they may produce what we call gamma ray bursts, which are very strong explosion of gamma rays, which are known from the 70s. We still don't know the progenitor. This is one possibility. And in principle, this will allow to check if this is really true.
More questions in the audience. There in the middle, I think. Well, next to you, Susan, there's a question there. Yes.
Yes, sir. I have this is kind of like an hypothetical question. I mean, obviously, according to Stephen Hopkins, the only way, maybe one of the mechanisms to lose that a black hole can actually disintegrate or emit some mass is by quantum tunneling. But it seems that this is another mechanism. If you have two black holes orbiting each other, is it a possibility? I mean, since you are emitting gravitational waves and actually you're transforming mass into energy and you're losing that mass, that there might be a transition between a black hole going back to a neutron star, and so on.
If I can perhaps slightly rephrase this also, I mean, I think there are many questions. Is there any impact on this, on the issue of kind of quantum gravity, something? Apart from, you're hesitant, Matias.
Perhaps you want to comment
No,
on this.
Was that the answer? No?
Well, I read that there were some statements about measuring the mass of the graviton. That so.
Yes.
That's
So that is so. What has been done is use the propagation of these gravitational waves, the time it takes for the gravitational waves to get to us. In particular, the time it takes for gravitational waves of different frequencies to get to us from this event, to constrain how gravitational waves propagate, and thus constrain properties of the graviton, which is the associated particle, and everything is consistent with just the waves that travel at the same speed for every frequency with the speed of light. Yeah.
yes, Scott.
So one of the great attractions, if you could perhaps localize the gravitational wave emission source and detect them with another telescope, basically what you would do is, if you got a gravitational wave signal, you would simply look with survey telescopes and see if you saw a flash of light from some galaxy in the survey area at exactly the same time. If you were able to do that, you'd be able to confirm that light and gravity waves travel at exactly the same speed, which is a natural consequence of Einstein's theory of relativity. But if you think about it without Einstein's insight, that would be a remarkable and surprising fact that these two completely different phenomena should propagate at exactly the same rate.
Nadia, you want to say?
Yeah, I will try to address the original question about whether or not there is a possibility of merging two black holes and then getting a neutron star out. So it's a complicated question, but probably the answer is no. And the answer, the reason I'm thinking that is that from the stellar evolution modeling that we do, we know that the black hole masses that result at the end of stellar evolution must be much heavier than the neutron stars. So the natural progression is, if you put more and more mass into the nucleus of the star, you get, as Doron explained, a white dwarf, which is big, then a neutron star, which is smaller, and the black hole, which is the densest option. And there are threshold masses for each one of those options. And the threshold for the black hole mass is called the Oppenheimer limit, is the highest one of all. So you're starting with objects that are most likely, at least 3 solar masses, and they're merging together. So the mass is 6, the combined mass of the star is 6 solar masses, okay? And you're going to lose some fraction of that energy to the gravitational wave emission. If we take lesson from this system, let's say 10%, you're still left with an object that's well above 5 solar masses, and our models suggest that neutron stars cannot exist at this mass. So that would be my gut level response to that.
I guess also Einstein's theory prohibited, right? So that's yes. question there, yes.
Yeah, in one of the earliest slides and also in the popular news media, there's a lot of details reported on the event. In particular, the distance, the total mass, and most puzzling to me is the distribution of masses of the two black holes. Could you say something about how these facts are determined, preferably a little bit more specifically than just it's a difficult calculation?
I want to echo this. So I think just the fact that so much information was obtained from what looks for the lay person as just a small wiggle.
Okay,
Matias.
I can say some about it. Some of it, in fact, is not a difficult calculation. So you, at least to get, so if you want to know why is it 30 solar masses as opposed to 100 or 1,000 solar masses, this is a calculation everybody that can still take the high school Newton's law thing from some shelf can do. Okay, so from the period of these oscillations, you know how long it's taking for the masses to go around, and they are also moving at the speed of light. So if you go to the Kepler's law and so on, and you find for something to be moving at the speed of light, and the time it takes to be the small fraction of a second that you can measure from the graph, just like that, you will come up with the 30 solar masses. Let's say if you assume the two are the same, you get 30 solar masses for each. So that part is just basically from the frequency of from the period of this oscillation, and the fact that it's moving at the speed of light, and you know it's moving at the speed of light because if not, it wouldn't merge in just a few oscillations. So with that information, you can calculate those two things. Then there's other information. The distance for the distance, the formula for the amplitude of this wave, I even wrote it down, which is just g Newton, the mass divided by the distance, and you do that calculation. You see the strain 10 to the minus 21. You figured out the mass from what I just told you. You plug it in, you get the 400 megaparsecs that they said. So all of those numbers are easy to get. The reason it's not so accurate, for example, the distance is that depends a little bit on the orientation of, and that is not so well known. Then other things like how much the final, if you want to know about the final spin of the black hole, you take the part of the signal which is decreasing, like it was a wiggle and then it decreased. So that decrease, there's two properties of this decrease. The period between the going up and going down, and how fast this decrease is. Those two numbers you can measure by eye, by seeing how, and that because black holes in the Einstein theory of gravity, they are all the same and described by just two properties, the mass and the spin. From those two numbers, that I can give you the formula, but it's not. You can get the mass and the spin. So from the decaying part, you get the mass and the spin of the final black hole from just looking with your eye. From the beginning part, you look from your eye and you know that they're going at the speed of light, they get the mass of the beginning ones. Then you can do it more accurately, and then you get it with like they do it. But to get a rough sense is not so difficult.
Can some of you say something?
I don't know what you mean by the distribution of mass. Oh, the mass ratio. Yeah. Sorry, that is more difficult because that indeed. So both the mass. So the easy thing to see is the total mass, or something called really the chirp mass when you look at the oscillations. Then it's more in the details. Two things are in the details that you need to compute to a higher order of precision: the spin of the original black holes and the mass ratio. Both of them create small effects in this that you can only do it by detailed calculation, and the signal is not so good. So those things are not so well constrained. So if you look in detail in the paper, it's not that they know that ratio so well. They know it goes in the following: this total mass, or really this chirp mass, is the thing which the signal depends the most. The first level of detail is the mass ratio, or and the next the spins of the incoming thing, and so you know this first thing pretty well because you can do it by eye. The next thing is in more detail. The third one we pretty almost don't know anything about that.
Can some of you say something about to which extent this is kind of a test of Einstein's theory of general relativity in a domain where we haven't tested it before?
Well, my personal, so first of all, my personal view about this event is that the detection of gravitational waves, is not all that interesting. We, as Nadia indicated, we already had incredibly strong circumstantial evidence that gravitational waves existed, and checks of Einstein's formula for the generation of gravitational waves that are far more accurate than we have at present from LIGO. Now, some people say, well, that was just circumstantial evidence for waves, but as Doron said, some circumstantial evidence is very strong, like when you find a trout in the milk. It's indication that the milk has been watered down. So we already had the trout in the milk. What's really, I think, exciting about the LIGO discovery is first, as Doron indicated, the existence of a population of objects in the universe that we had no idea, had no direct evidence that they existed. And the second is the prospect that as LIGO continues to watch, it will detect black hole mergers with higher signal to noise that will eventually permit more and more accurate tests of Einstein's theory. And in fact, the concern is that if LIGO sees some signals that have really high signal to noise, that will erode the science case for LISA, because it will already provide a test of general relativity that will confirm it in these extreme conditions beyond any reasonable doubt.
Thank you. Perhaps as a final question, I want to ask all four of you. So I hope you agree that this was an exciting discovery, and it caught the imagination of many. Scott, you already say that for the future you expect things to be exciting, but not too exciting. So that is still a case for next round of experiment. Just each of you want to ask you what from your point of view would be kind of the most exciting thing that will come out in the next year or two. What are the things that you personally are looking forward, Nadia?
Well, I'm personally very interested in supermassive black hole binaries, so that is perhaps a little bit further away on the horizon of, as we discussed. So there is this tantalizing issue that the sensitivity of the pulsar timing array is already in the right ballpark and we're not seeing anything. LISA is a little bit further away for detecting the final merger event. Well, I personally think that, a merger of 2 billion solar mass black holes is an absolutely fascinating event. So there's a lot of
Can't get much bigger, right?
Exactly. There is a lot of research going on in the electromagnetic wave astronomy. So now I have to preface that with an actual qualifier to try to look for candidate objects. So including some of the stuff that I've been involved in. But we do see that galaxies merge. We do know that supermassive black holes exist in centers of galaxies. And so we do know that the binary black holes must form. What we absolutely don't know is whether or not they spiral in and ultimately merge. So to me, this is a fascinating question, which perhaps might be answered within the next few years.
And this would then pale in comparison, right? That's Scott, what's your
well, the event
dream scenario?
The event we saw last week was a signal to noise of about 20. I'd like to see in the next year a similar event with a signal to noise of about 50 that doesn't agree with Einstein's theory.
Matias.
Well, I think that this machine turned on, and the first thing we saw was something that we didn't know it even existed. So I'm hoping that more things that we thought didn't even exist will show up, and some of which might have to do with cosmology or with anything else. I think we've opened up a new way of looking out, and I'm hoping that and we know that to produce these things is require very extreme conditions and phenomena. And so we think that we can figure out what's going to happen and what's out there just by thinking, and in many cases that's true, but many times it's not the case. And so I'm hoping that with this new opportunity, new objects, new strange things will emerge.
Doron, final words for you.
I think if to be realistic in the next few years, we just have more of these black hole systems. I try to imagine what will be really outstanding. I think if the spins could be measured very accurately, and for example, they're going to turn out very small or something like this, or very large, this will have some immediate consequences. I think what really LIGO can hope for is neutron star plus black hole merger and electromagnetic counterpart, which will be, I think, very exciting.
Well, perhaps just kind of summarizing, so thank you all for being here. Now, often we look back at certain historical developments and we just wonder, I just wish I was living in that exciting period in the 17th century or when quantum mechanics was born. I think one thing we learn here that, in 100 years people say, oh, the people living in 2016, they were extremely fortunate to be a part of and witness at that revolution. Thank you for being here. There's a reception in Fould Hall and hope to see you all there. And please give a warm word of thanks for our speakers.